Hello, everyone. Can you hear me?
Yes.
Yes.
Okay, but only 4 of us as yet. Is it because there is some conflict or why?
Yeah, some students said that they have an overlap in their schedule. So
Oh, that's a
at least
problem.
two I remember.
Yes, and I will ask. I will ask the Department for Education to move this time permanently because at 12:40 I have an overlap with important meetings which I can't skip. They are so important that I would rather move a lecture but still attend the meeting. That's why. Okay, we're joining slowly but surely. Let's wait for a short while further. And we'll start in possibly 2 minutes. Okay, let us possibly start, and the lecture will be available in a recorded form anyway, so anyone who missed it would be able to see it later on. Okay. Okay, you got the whiteboard, right? Can you see the whiteboard?
Yes, we can.
Okay, great. So, today is the second lecture on elliptic curves. You remember last time there was a recap of private and public key cryptography in general, and then we moved to elliptic curves. And today we'll study the theory of elliptic curves a little bit further. We'll consider elliptic curves over finite fields, and we will see the actual application of them, which is the elliptic curves digital signature algorithm. As you will see, although they look quite sophisticated, but in fact, they are to some extent more simple and more computationally easy to implement, and in general require, with the same level of security, a smaller key size, and that's probably the main advantage compared to the classical RSA algorithm. And that's why they're so popular. So I would like to mention that what we are doing now, and you will continue in your labs, you will implement some elliptic curves algorithms in your favorite programming language, possibly C or C++. this is not just an academic exercise. A lot of real implementation work for blockchain technologies does require implementation or re-implementation of certain elliptic curve type algorithms. You can, of course, use existing libraries, but very often you would need to implement something from scratch, either for the reasons of efficiency or because you would use some kind of non-standard hardware or anything like that. So a hands-on experience with arithmetic of elliptic curves and how to use them and what it all means is quite important. Okay, so as you remember, an elliptic curve has nothing to do with ellipses which are second order curves in the plane, right? Rather, these are curves of degree, of which degree?
3.
3. They are cubic curves, yes. Y squared equals to x cubed plus ax plus b under some genericity conditions, if you remember, imposed on the coefficients, all right? So if these genericity conditions are not fulfilled, then an elliptic curve may have a cusp or it may have a self-intersection. So for example, having both coefficients equal to a and b being equal to 0 is actually no good. Okay, so as we saw, an elliptic curve could be just a one continuous branch, or it could consist of two separate branches. Let us draw up an example which is entirely continuous. So you see, as it is symmetric, obviously, over the x-axis. Y symmetric, because if we solve it for y, it will be just plus minus square root of the right hand side, all right? We know that it tends, as x tends to infinity, then y asymptotically behaves as x to the power 3 over 2 plus minus x to the power 3 over 2. So these are asymptotic orders of growth of the curve as x tends to infinity. We introduced the notion of, actually I wouldn't call this point O for origin, because the elliptic curve has another 0 point which is not in the origin. It is an infinity point. So let me call this point, for example, O prime, which is the origin. And the point which we denote by O is at infinity. And you can think that the curve is a closed one coming through the infinity. Okay. So then we introduced, if you remember, we introduced the notion of addition of points over the curve. So suppose that, disregard this, it is just accidental garbage which occurs when I press the wrong button. Suppose that there are points P and Q on the curve. Then in order to construct the sum P plus Q, what do? You remember? 2 points on the
Put
curve.
a line with 2 points
Draw.
and mark an intersection.
Yes, we draw a
Curve.
straight line. We make an intersection. Let this be a point called R prime. And then
And
we take
reflect.
symmetric point with respect to R prime, which is R. So basically R is P plus Q, whereas R prime is such that P plus Q plus R prime is assumed to be 0, where 0 actually means infinity. Infinity plays the role of the 0 point in this very strange addition. And obviously, if we assume that P plus Q plus R prime is 0 and symmetry with respect to the x-axis is negation, therefore R is supposed to minus R prime, then this means that R is exactly P plus Q. Okay, how would we construct this point R prime and then R algebraically? That is a bit interesting. So let us see. So what is known? Suppose that we have points P with the coordinates xp, yp, and q with coordinates xq, yq. Okay? First of all, what do we know about them? That they satisfy the elliptic curve equation. So yp squared equals to the constants A and B are known. These are fixed constants, so we do know them. Yp squared is xp squared plus a xp plus b. Yq squared is xq squared plus a xq plus
Cube.
cube, not squared. You are right. Xp cubed, xq cubed. All right, thank you. Now, what do we know about R prime? If we draw a line through PQ, then this line has the inclination to the x-axis, the tangent. Let me denote it by S, which will be, just a second, I apologize, I respond to a very urgent call. Добрый день. Да, здравствуйте, здравствуйте. Я прошу меня извинить, я сейчас лекцию читаю. Если там ничего срочного нет, можно я вам перезвоню после лекции? У вас вопрос, конечно, по там завершению материалов, да? Да, буду. Да, ну сегодня завершу, хорошо? Да, спасибо. Окей, спасибо. Окей, спасибо. Okay, my apologies. Okay, so then the tangent of this line is, obviously you can say it is yp minus yq over xp minus xq. Okay, and then the whole line can be represented as y equals to sx plus some, let's say, d. Okay, then we can say that in particular for xr, a similar equation should hold, that first of all, obviously they are connected through, let's say for r prime, we'll do it first for r prime, that it lies on the curve. Therefore, y squared r prime equals to x cubed r prime plus a x r prime plus b. On the other hand, it lies on the same extension of our original line with the tangent equal to s. Therefore, we can say y r prime equals to, for example, x times s times x r prime minus, for example, xp plus yp, because same equation can be written as s times x minus, for example, xp plus yp. Okay, so what do we have? We basically have xr and yr unknown. Okay. Given that we found xr, yr is very easy to compute. But effectively, this means that we have to solve these two systems of equations with respect to unknowns xr and yr. One of these equations is linear.
Excuse me. May I ask the question?
Yes, yes, please.
Why do we subtract? Why is it equal x is equal to x minus p and d becomes yp?
Okay. Suppose that it is indeed y equals to sx plus d, where s is the tangent to inclination of this line. Now take any base point, really take any base point. For example, take xp, yp. Then from this equation we have yp equals to sxp plus d. From this, it is immediately clear that d equals to yp minus sxp. And substituting d into this equation, we have y equals to sx plus yp minus sxp, or factoring out s, we'll get s times x minus xp plus yp,
Okay, got it.
or xq yq to that end. Okay, so yeah, basically, this free term can be written as d, or it can be written in terms of any point which we know lies on the curve. Okay, then basically all coordinates xp, xq, yp, yq are known. From them, s is known. Okay, s is known. Therefore, look at the last two equations here. So in the left-hand side and in the left-hand side there is y r prime. In the right-hand side there is a cubic or linear polynomial with respect to x r prime. How can we solve this system? We need to solve it with respect to x r prime, y r prime. Well, the easiest way is probably to substitute the second equation into the first one. All right? And then what? Then in the left-hand side, there will be some quadratic polynomial with respect to x. In the right-hand side, there will be a cubic polynomial of the highest degree 1 with respect to x r prime, right? So we have, in fact, a third degree equation in x r prime. Well, you probably know, you have seen either at school or maybe here at the university or somehow, that in addition to being able to solve quadratic equations, everyone remembers this from school, we can also solve equations of degree 3 and even 4 in closed form, in radicals. In particular, the formula for solving the equations of degree 3 is called the Cardano formula. Have you seen that?
Yes.
Okay. But, you know, if it comes to the point that we need to apply the Cardano formula, it means that we got into something really tedious, and it is not really what we want. We would have to do it, but there is actually a much more simple way of how we can solve these equations. And we'll do it now, I would say, in a much more easy way. What helps us is that S is a function of xp/yp, but xp/yp are not arbitrary. Oh, and xq/yq. They are connected by this first pair of equations. And actually, the fact that there are connections between xp/yp, xq/yq significantly simplifies our task. And it is not even necessary to use this formula. So, to use the Cardano formula, everything will be much more simple. So indeed, for any point xy which belongs to, let me denote this elliptic curve by maybe E, which belongs to E and which belongs to the line, the following conditions must hold. That really substituting the y from the line is sx plus d. So sx plus d squared, which is y squared, must be equal to the right hand side, x cubed plus ax plus b, correct? Or moving all terms into the left hand side, well, into the right hand side, and then swapping the left hand side and the right hand side, we would eventually get x cubed. The quadratic term is only formed by sx plus d squared. Therefore, it would be minus s squared x squared, correct? Plus a minus 2 times sd x plus b minus d squared equals to 0. And now a magic trick. We know that this equation holds for xp, because xp, yes, lies on both actually the elliptic curve and the straight line. xq for the same reason, and must hold for xr prime, right? Okay, so this means that xp, xq, and xr prime are what? Are roots of the left-hand side. Correct? But if we know that these are 3 roots of a cubic polynomial in the left-hand side, then the left-hand side can also be represented as a product of x minus xp, x minus xq, x minus x r prime. And that should be equal to 0, identically. Of course. xp, xq, xr prime are the roots. Okay? So basically, this star and this factorized representation of the left-hand side must be the same polynomials. So now we can expand this. This means that expanding makes x cubed minus, that's Viet formula actually, minus xp plus xq plus xr prime x squared plus, now the terms at x, they would come with plus because from each bracket we have x, and from two others we have a product minus, for example, xq minus xr prime. Therefore, it will be xp xq plus xp xr prime plus xq xr prime times x, and minus the product of the roots, xp xq xr prime equals to 0. But we can now equate the coefficients. At x cubed, the coefficient is 1. Now by equating the coefficients at x squared, we immediately see that s squared equals to xp plus xq plus xr prime. That the coefficient at x is equal to a minus 2 times sd, but it doesn't really matter that much for us because our problem is already solved. So from that point of view, making this trick, we immediately see that xr prime is just s squared minus xp minus xq. And then once we got that, we, in the standard way as before, we derive from the linear equation y r prime, which you remember was s times, for example, x r prime minus, for example, xp plus yp. So that's the solution in the generic case. This is a generic solution. We don't need to do anything more. Obviously, the solution is a non-linear function. That's important. All the coordinates of the original points, because s, if you remember, s was yp minus yq divided by xp minus xq. So, under the genericity conditions, we have this solution, and the solution is a finite point. Sometimes the sum of 2 points is indeed 0. You remember that 0 is actually, in our terminology, actually to make things a little bit more clear and to distinguish our 0 on the curve from 0 in the origin, let me call it not 0 but theta, which is a similar symbol as we do in algebra. So you know it is something resembling 0, and it is treated as 0, but it is not the same as 0 in the origin. Okay, so that's theta. Okay, what do we need to have in order to get theta as a result? Obviously, as long as s is finite, then we have finite values for x r prime and y r prime, provided that, of course, x p and xq are finite. But it may happen that xp equals to xq. So that's the generic solution. S is computable if xp is not equal to xq. If xp equals to xq, then there are two possibilities actually. So let me call the generic case to be case 1. Case 2, when xp equals to xq, would be the degenerate case. Okay. But there are actually two degenerate cases. Can you tell me, please, why two? What are the two degenerate cases? 2.1 and 2.2. Let's look at this expression. Okay, the denominator is 0, so there is really singularity. So something is wrong in that case, and we cannot compute the finite s. But there are two possibilities. The first case is when yp is not equal to yq, which means that the numerator is non-zero, the denominator is 0. Okay? Actually, when yp is not equal to yq, whereas xp is equal to xq, let's have a look at our curve. So for p and q, x values are the same, y values are not the same. If x values are the same, then this means that these are opposite points, right? These are just opposite points. So suppose that there is a p here and q here. Let me call it p1 and q1. And then the sum of such points is indeed, how do we denote the sum of such points? They're opposite to each other on the curve.
0.
Theta. 0, yes, in our
Theta.
algebraic notation, but we can call it theta, yes. In this case, we have p1 plus q1 equals to theta. Okay? And indeed, theta means at the same time, geometrically. So there is a different notion of the geometric and algebraic notation in theta. Geometrically, theta is located at infinity, right? But algebraically, it plays a role of 0 in our addition. Why? Because we defined addition of points in such a peculiar way. So it is 0. Geometrically at infinity, algebraically 0. So the infinite point, infinitely remote point, plays a role of algebraic 0 in our definition of elliptic curve separation. And indeed, yp not equal to yq, the denominator is 0, the numerator is not 0, which really suggests that s equals to infinity, which is consistent with the fact that p plus q, in this case, is theta at infinity. But a completely different situation occurs if yp equals to yq. That's case 2, xp equals to xq, yp equals to yq. Therefore, p and q are the same, right? So effectively, you compute a point which is 2 times p. Okay? We're computing 2 times p. What can we do in this case? Well, and obviously, P plus Q is theta in this case. In the first generic case, we have for the actual point R, XR, YR would be equal to, you remember we need to do a reflection with respect to the x-axis, so it will be XR prime minus YR prime. So this is not the sum yet. The sum is obtained by reflecting XR prime, YR prime with respect to the x-axis. So let us consider this case 2.2 in more detail. So basically, there is nothing that much degenerate about it. What happens is that, suppose that we have points P and Q very, very, very close to each other. For example, P2, Q2. And we move them towards each other until they meet. And in that case, it is no longer possible to draw a line from P to Q which intersects our curve, but you understand that if these 2 points approach, 2 points on the curve approach each other, then eventually we get a line which is tangential to the curve, right? When P and Q are become the same, which gives us a slightly different formula to calculate S. We can't use the generic formula in that case. What should we do? How do we calculate S in this case? If we consider these points as one of the points as a limiting case of the other, so for example, we say xq equals to xp plus dx, yq equals to yp plus dy, and dx dy tend to 0 while still on the curve, okay? Then we can say that yp plus dy squared equals to xp plus dx squared plus a times xp plus dx plus b. And for yp squared itself, we have xp squared without dx plus axp plus b. Okay? Now, using the standard differential calculus, we can say that as dx dy tend to 0, we can say that yp plus dy squared can be linearly approximated as yp squared plus the derivative of the left-hand side 2 times yp dy, xp, sorry, cube again. What am I doing? Cube, of course, cube. Xp plus dx cubed, xp cubed. Xp plus dx cubed can be approximated as xp cubed plus 3 times xp squared dx. And then subtracting one equation from the other, we would obviously have two times yp dy equals to 3 times xp squared dx plus a times dx. Or factoring out dx, it would be 3xp squared plus a times dx. And then our coefficient s, which is the tangent of this PQ line, would be precisely dy dx. And from this, it is clear that dy dx is 3 times xp squared plus a divided by 2 times yp. Okay? Which means what? We have resolved the singularity in this particular case. Resolve the singularity. It used to be a singularity 0 divided by 0, when both actually the numerator and the denominator of the generic formula vanish. We constructed a limit. Okay, and once this singularity is resolved, it is easy to see that all other formulas are again applicable straight away. So for example, in the original case, we had, if you remember, x r prime was equal to s squared minus xp minus xq, but in this case, xq tends to xp, and therefore it becomes xr prime equals to s squared minus simply 2 times xp, where s is now given by this expression. Okay, so that's how we resolved all cases, and we defined our arithmetic operations over our elliptic curve. Obviously, yet another degenerate case, very degenerate, but we need to take it into account. Case 3, if, for example, let's say Q is theta, then we define any point P plus Q to be P itself. Okay, so this is a very oddly, but nevertheless defined addition of points over our curve. Okay, really strange, really odd, but that's how we define it. Moreover, what can we say? So properties of addition. By definition, we can say really yes. So for any p plus theta is p. That's by definition. Now, Interestingly enough, so this means the notion of a zero. There is also a commutativity property. P plus Q is the same as, interestingly enough, Q plus P. Why is that? Why do you think this holds? Because the ordering of points, which one was denoted by P and which one by Q, didn't matter at all. If we look at our final formulas, then let's see. The value of S is symmetric with respect to swapping P and Q. If we swap P and Q, then both actually, in the generic case, the numerator and the denominator change sign, and therefore S remain the same, right? Furthermore, the expression for xr prime is again symmetric with respect to xp and xq. You simply subtract the sum of xp and xq from s squared. And you can very easily see, because both points lie, all 3 points lie on the same straight line, that equally you can write for yr prime the expression that it is s times x prime minus, for example, xq, if you hold xq for the base point, plus yq. Therefore, in the generic case, our formulas are completely symmetric with respect to P and Q, which means that we can swap the role of P and Q and still get the same result. Now, in the degenerate case, let us consider our final formulas for the degenerate case. But in the degenerate case, it is the same point P, which can of course...
Excuse me.
Yeah.
If we are talking about addition operation, if we can swap elements, does it mean that operation is commutative?
That's what I call, yes, addition is commutative. Yes.
Does it mean if we will extend this, we can say that on elliptic curves we may define the field?
We are about to do it, but you are almost right, not exactly, because in order to define a field, we would need also multiplication and division, which are not different.
Yes.
But
no,
we can
but
define
at least we can define something.
Group. It is called a group.
Some group.
Yes, this algebraic structure is called a group, but we're not there quite yet. So we will do it very shortly. That is actually my objective. You are absolutely right. Yes, but not exactly. So the operation is commutative. So I put it here, commutativity, we know. But actually, to define a group, commutativity is not required. So you know, for example, that all non-singular matrices, square matrices, of size n, which have non-zero determinant, they follow a group, a multiplicative group. Instead of addition, we consider the operation of multiplication, actually additive group as well. But a more interesting is a multiplicative group, in which case the multiplication is not commutative. But in this case, it is. There is something more, which is required in order to prove actually that it is a group, that addition must be associative. So basically, if we have P plus Q plus R that way, this must be equal to P plus Q plus R. And this is quite non-trivial. the only thing we have seen so far is that really if P plus Q plus R results in theta, and that happens when all these 3 points lie on the same straight line, right? Then indeed it doesn't matter in which order we perform addition, because actually we can take any pair of points, it will be exactly same straight line, and therefore the third point would add up to 0. So this is trivial if the sum is theta. Needs to be proved, needs to be proved must be proved in the general case. There are several proofs available. By the way, they are non-trivial. I will not dwell on them in detail. So yes, it can be proved. Can be proved, for example, algebraically using the formulas we have developed. But tedious. So we take it without a proof that associativity also holds. And then yes, points on our elliptic curve E form a group. Yes, and in addition, apart from addition, we have negation. Points x, y become x minus y, so negation is only with respect to y, and then xy plus x minus y is actually theta. So yet then points on our elliptic curve E form a group. This group is, first of all, because the operation is commutative, it is called abelian. After the 19th century mathematician Abel, who first started commutative groups. And secondly, this group is additive. Simply because the group operation is plus in this case, not multiplication, but plus. Although it doesn't matter, we can denote it by any symbol. All right? But what we do can be conveniently explained as addition. Group operation is plus. Is called plus, but it can be called any. Okay, so that's indeed a group property. Okay, it is not a field, it is not a ring, because we define only one operation. We define addition of points. We do not define. Can you hear me? Excuse me, can you hear me? I had a split-second power cut. Can you hear me? Okay, can you hear me now?
Yes.
I apologize, I had a split-second power cut, but that was sufficient for my router to go down, and then it took a little while for it to get back. Okay? I apologize. So you can see the screen, right? We stopped at the point that it is an abelian.
Not yet.
Yes, abelian and additive group.
We cannot see it.
Ah, you cannot see it. What about now?
It works. Thanks.
Yeah, it works.
One of the explanations is that there is an illegal mining farm in the apartment block where I live. That's why there are power cuts. By the way, that is directly related to the subject of our lecture, all right? Okay. Then it is a group, and we can do the following. So, for example, if we fix a certain point on the curve, suppose that there is G, a point which belongs to our elliptic curve, a fixed point. Then we can define an operation NG, where N is a positive integer, which is G plus G plus G n times. So this is a multiplication of a point by an integer. Which is relatively easy to compute. Not very straightforward because we still need to perform all those operations that we previously discussed, but it is a relatively easy, relatively straightforward to compute. And obviously, in order to do that, you may use a much more powerful algorithm than just a direct addition, right? So you can, instead of doing n operations, you can only do it in log n operations, all right? Do G plus G, then double it again, you would have 4 times G, then double it again, you get 8 times G, and so on. Okay? And for large n, that's precisely the way of how it should be implemented. I think in the next lab, your task will be precisely to implement, given a certain elliptic curve, to implement multiplication of points, multiplication of a point by an integer. Okay. What is interesting is that it is much more difficult to compute the opposite operation. So this is straightforward. But going back from NG to G, if N is known, is much more difficult. And it is even more difficult if we compute instead of using real numbers or computer representation of real numbers, which are floating point numbers, if we compute our elliptic curve over a field ZP. So now assume that we are doing ZP operations.
Excuse me. What is difficult to get from NG to get point G or to get number N?
No, suppose that N is known. N is known. From NG, it is more difficult to get G if N is low.
Okay.
And
Thank you.
nearly impossible, well, absolutely impossible given current technology, if calculations are in addition performed over a finite field like ZP. For finite field, what would happen is, let's get back to our drawing. You, of course, remember, everyone remembers what is ZP, which is the field of cosets modular prime P, right? Then the smallest P is 2, of course, as the smallest prime, but P can be very large as well. That such operations, modular P, do indeed form a field. And we discussed last time why, because if P is prime, then you can define the inverse operation over this inverse operation modular P. So for any, let's say for any Q, which will be in the range, let's say 0, C plus 1, you can define the inverse Q such that the inverse Q times Q equals to 1 modulo P. And this is done using the extended GCD algorithm. You remember we discussed it last time, because it allows us to compute this GDP of PQ, which is of course 1 because P is prime. But on the other hand, once we compute it using the extended GDP algorithm, it would be represented as A Q plus BP, and therefore the inverse Q or inverse of Q is precisely A modulo P. All right? So that's how that P works. In general, a finite field doesn't need to have a prime order. There are also fields, as we mentioned, Galois fields. Gf of P to some power n. So in general, instead of ZP, we can consider elliptic curves over Galois fields, but this is currently considered to be unnecessary. Galois fields are much more useful in encryption algorithms like AES, when we need to, for example, invert arbitrary bytes, which have 2 to the power, for example, 8 values, and then indeed there exists a Galois field of that size, whereas obviously 256 by itself is not a prime, and that's why it cannot be a field ZP. But for elliptic curves, so I would say this is rarely used for elliptic curves. Simply not necessary. Whereas arithmetic over ZP is very widely used. As we know, all elements of this field ZP are in the range from 0 to P minus 1. Okay? Therefore, if we perform operations, for example, it happened that, and the integers, obviously you need to consider the coefficients A and B to be from ZP as well. If it comes to, let's come to the original formula. In this case, the coefficients A and B would be from ZP as well. And we are only interested in those points which have, in that case, ZP coordinates, which means that, by the way, in that case, the curve cannot grow to infinity geometrically. So instead of a continuous curve, we would have just discrete points with integer coordinates belonging to ZP, with both actually x and y limited to a range from 0 to p minus 1. Okay, so any larger values, if they occur, they are mapped back into a range from 0 to p. The negative values, there are no negative values anymore. They are mapped into a range from 0 to p as well, by simply adding a multiple of p. And therefore, in this case, over ZP, how would it look like? It would look like a square area in both x and y from 0 to p minus 1. So you can construct such a grid, and some points on this grid, they belong to our curve, some are not, but due to modular arithmetic, points can be, there is no even a remnant of just some kind of consecutive curve, because our points can be arbitrarily mapped inside this 0 to p minus 1 square, and therefore our elliptic curve is just a collection of some points inside 0 to p minus 1 square, which belong to this curve. Okay, so there is nothing like this anymore, but the rules of constructing sums of the points are still the same. Only there is no such a nice geometric property anymore, but the rules are exactly the same. So the question is, how many rational points, actually with coefficients belonging to, how many ZP points an elliptic curve might have in general? It is a very good point, very good question, because actually what we are going to do is to do cryptography with those points. So this is this collection of ZP points is actually our elliptic curve E. Then we select a certain given point G, and our public key cryptography and digital signature algorithms based on G are precisely based on the notion that, yes, we are going to construct multiples of G, G plus G plus G plus G, which will be jumping over those points, but the inverse operation will become very difficult computationally. So it is very difficult computationally only if the number of points here is large. So the question is, how large is the collection of points, elliptic curve points over ZP? What is your idea? Roughly, what can we say? How many points? Well, how many different axes we might have? The maximum value of axis is p, from 0 to p minus 1, the discrete values, right? So eventually it will happen that for large p, that if any x is mapped to any y, then we would have roughly at most p squared points, right? P squared. But because it is still a curve rather than a two-dimensional area, then we wouldn't expect a square number of points. Rather, I would say would still imagine and expect a linear number of points in P. And indeed, there is a Hesse actually in German theorem. Hesse theorem, proved long time ago in 1934, that the number of points in E is roughly equal to P, or more precisely, the absolute value of the number of points minus P plus 1 is less than or equal to 2 times square root of T. So the deviation is quite large, as you see. So on average, it is, let's say, P plus 1, but it can deviate from that value by plus minus 2 times square root of P. Obviously, as P tends to plus infinity, then it is this central estimate P plus 1 dominates the interval size. So the relative discrepancy becomes smaller and smaller and smaller. It will be like 2 square root of P divided by P plus 1, which tends to 0 as P tends to infinity. So that's the number. And this means that if we have P large enough, what is P large enough? Say 256 bit, not around 256, but 256 bit. So approximately of the order of 2 to the power 256. Okay? 2 to the power 56 is what? The decimal log of 2 is about 0.3. Therefore, it is about 256 multiplied 10 to the power 0.3 times 256. Therefore, it is about 10 to power 80, something like that. Okay? I deliberately do not compute it more precisely. You can do it. Which is a huge number of points. So then it means that direct exhaustive search over this number of points is not possible. With the current state of technology, we say for cryptographic purposes, for digital signatures, for example, any number of points which is greater than, let's say, 10 to 60 is perfectly okay. Which means that we can use, for example, a 256 size, 256 size P in our computations, and it is generally okay. Whereas in RSA or DSA, based on the number factorization, as we discussed in the previous lecture, we currently, in order to make sure that it is secure, we need to use much larger key sizes. So you remember that 1024-bit RSA is currently considered to be totally insecure, and you need probably a double of that. So for RSA, let's say 2048 bit is required. Then the explanation why elliptic curve cryptography is so much used, so much preferred nowadays. It can be used in a number of algorithms. It can be used in, for example, SSL, SSH. It can be used in digital signatures, in blockchain technologies. So almost everywhere it has some advantages over the classical RSA. So what do we do in order to implement digital signatures with elliptic curves over ZP? What do we do exactly? Let's see. Digital signatures using elliptic curves over ZP. This will be based on the operation which I mentioned actually. Making a multiple of a point is easy, but finding the number itself, actually performing division by n, is extremely, extremely, extremely difficult. So first of all, what do we need to do in this case? Given E, the curve, which actually means, what does it mean the curve is given? Can you tell me, please?
Parameters of A and B.
Yes, A and B. A and B are given. You're absolutely right. Now, the other thing we need to have. We have some point G, which belongs to E, point on the curve. Actually, I would like to mention that we need a very, very special point on the curve. There is a thing which is called the order of the point. I will explain what it means. N order or order of G. By definition, it is the minimum. N is minimum N, such that N times G is theta. Well, why such an exists in the first place? Because we have, in that case, a finite number of points. So these points, they form a group, as we have already seen. So if we start adding and adding and adding them together, then at some point, we must encounter, well, a point previously already seen. It doesn't necessarily mean that we encounter theta, but it means that the number of points cannot go to infinity, because overall there is a finite number of points. And we can prove that, well, in particular, we may encounter not actually for any point it would be. We may, for example, in a very odd situation, find a point such as a point G, such that which is not theta itself, that is 2 times G is, for example, equal to G itself in some very, very, very degenerate situations, possibly. Although it is a question actually whether it may exist in real situations. But the order of the element is indeed the minimum n such that n times g is theta. And we will require that, first of all, it is an element of a finite order, yes. And secondly, that n is prime. So basically, we need a curve, a point on this curve of a prime order, so that n times g is theta, and n is minimum with this property, and n is prime. This is not always the case. But there is an algorithm which allows you to construct actually such a curve. The curve can be arbitrary, so you are not you do not care very much about the values of a and b. So, for example, it is called Baroque Stephen Hagen algorithm. Given n prime, it constructs not for arbitrary p, but given n prime, it constructs for you p and e such that actually it has even a better property, such that the total number of elements in this curve over the p, of course, is n. If the total number is n, the whole group is of prime order, and it is very easy to see that in that case, we can actually take any element of that curve, and it would have the desired property. Then any g which belongs to this e is okay. Ng would be equal to theta. Why? Because there is a theorem from the group theory that the order of any element is actually a divisor of the order of the whole group. But in this case, the divisor, the order of the whole group, n is prime. Therefore, for any element, the order of the element is either n or 1. It cannot be 1 because then it is theta by itself. Therefore, the order of any element is n. Okay. So such a curve and and p can be constructed for a given n. Okay, we'll use it. So then, that's precisely what we need. And then the digital signature algorithm is the following. Yes, in addition, we need something else. We need some private key dA, which is again some point on our curve. Sorry, not a point on the curve. I apologize. This is a number. My apologies. DA, the private key, is a number. It will be used as a number of times we are going to perform multiplication. So DA is a number which belongs to the same ZP. ZP, not curve. Private key. And our public key, will be actually a point, QA, which is DA times that fixed point G. G is known. DA times G would be a public key. For a large DA, as we already know, it is not possible to reconstruct DA from QA. Then, given a message M, which is considered to be a bit string, we first construct some hash. Using whatever cryptographically strong hashing algorithm is available. For example, SHA, I don't know, SHA-1 is not cryptographically strong, SHA-2 maybe is okay. This hash algorithm does not make part of this digital signature by itself. We just need it to be strong enough. Crypto strong hashing algorithm. So the first step in digitally signing a message is to compute a hash. Why? Simply because that way we compress the whole message, which can be large, into just a hash. So we sign not the message itself, but we sign a hash of it. With a good cryptographically strong hashing function, the probability of collision that two different messages would have the same cache is absolutely infinitesimal, and it is not possible to generate those collisions deliberately. Okay, then we have, for example, if our AP is, let's say, 256 prime, let's say ln is a bit length of, let's say, of n. And n is the total number of elements in the group. You remember that it is more or less not exactly the same, but it is of the same order of magnitude as p in that p, but not necessarily the same. Both of them are prime. P is prime, we used it for arithmetic, and n is the prime order of our group, but they are not the same. They are comparable by the order of magnitude. So if ln is a bit length of n, then we take, let's say, we take z ln leading bits of e. So basically, it is like this. There is a long message m. By applying a hash function, we get a shorter hash of a certain length, and then we take the initial ln bits, and this is our z. effectively, it is just hashing and taking as number of bits as we can process. A hash can be longer. Never mind. We take the leading. It is just considered to be slightly more cryptographically secure to take the leading bits rather than the trailing bits, although it doesn't probably matter that much. Now, so basically what we need to now digitally sign is this Z, which is obtained by this two-step hashing of our message. How do we do it? Very important point. Now select, we do not apply our private key directly. That would be a grave error. What we do, we take K, which is a random number, and that's very important, a random number from 0 to n-1. And it is very important, actually, a number of algorithms badly designed were correct when K was not random enough, or indeed in one very particular implementation for Sony PlayStation, it was a constant. And then, although this constant was not known and it was deeply embedded in this cryptography software, it was very easy to actually reconstruct it, how I will show. But now we say it is random. So this is a one-time addition to our private key, I would say. Then we consider computer point with coordinates, let's say x1, y1, which is simply k times our point g. Okay. Then y1 is dropped. X1 is processed further. We want this x1 to be non-zero. If it is 0, we just reiterate our generation and take another one. Say it is non-zero. Then we compute R, which is simply x1 modulo n. And we compute S, which is the inverse of K, of that K, of Z, and Z is precisely our truncated hash. So that's precisely what we really need to sign. Plus previously computed R times our private key DA, all again modulo n. And the digital signature is made of those two values, R and S. Now, how to verify this digital signature? That's pretty much easy. Some technical checks. So again, in order to verify, we take our message M, compute E, which is the hash of M, compute Z, which are leading ln bits of E. Same as here. So we are dealing with the same Z as it was in the forward operation. We just need to compare signatures. We now compute the following quantity. Let's compute a point C on the curve with the coordinates x, so let's say x1, y1, which is taking 2 points. One of them is z times inverse of s, where s is a part of signature, times g, plus another point, which is r times inverse of s, again, times our public key QA. Both points G and QA are known. That's perfectly okay. And then that's basically the final thing. What should we get as a result? We must have, for the correctness, first of all, x1 must not be equal to 0. And more specifically, x1 must be equal to r. If it is okay, then signature verification succeeds. Why is that? It is very, very, very easy to see that just by continuing this way, okay, what is, according to our definitions, what is, okay, z is our value, but what is actually the value of r? So s is, okay, you can see this point x1, y1. If it is computed this way, it is inverse of s times actually z plus rga by construction, and eventually times g, and eventually this means it is k times g, and therefore it is precisely how our point R was constructed, because if we look back here, that's precisely what the original x1, y1 was and how we obtained R from it. So verification is easy. So if this succeeds, then our signature is valid. If not, then the probability of a collision is absolutely infinitesimal, and therefore we can say that the operation fails. So that's basically all. We have already overspent 15 minutes. I apologize for that, although we started slightly later. This will become more clear when you actually implement this algorithm in a lab. That's what we're going to do. For the moment, just are there any questions? Tell me, please.
Will we have this whiteboard as a separate file?
A separate file for the whiteboard. So you want or you do not want a separate file?
I mean, I think it will be good to be possible to see this board without the video.
Okay, I think for the previous lecture it is the case, and the whiteboard is available. If you look in Moodle, I think the whiteboard is there. And for this lecture, it will be in as well.
Okay, thank you.
Okay. So thank you. We are done for today, and think about it. look at formulas, try it for yourself, see how it works, and then be ready to implement it in labs. By the way, what is your favorite programming language? So would you like to do it in C, C++, Python, or how would you like lab setup to try it out?
Usually we did all the cryptography stuff in Python, so probably it will be the best case for everyone.
In Python, which library for large integer multiplication and so on, like large integer arithmetic or ZP arithmetic, did you use in Python? There are several of them.
I believe most of people either didn't use anything because like from the standard library, it works pretty well. And there is like crypto and NumPy.
Okay, so, okay, either standard library or crypto or NumPy. Okay, we'll see. Okay, we're done. Thank you. If no more questions, we're done for today. Thanks. Bye.
Goodbye.